Hello students, and welcome to this lesson on equilibrium, acids and bases. The big question is, what is equilibrium? Well, very simply stated, it is when the rate of the forward reaction becomes equal to the rate of the reverse reaction. So the new concept here is that reactions can go both forwards and backwards. You think of forwards reactions like burning homework. Why anybody would ever do that, I do not know. But if you were to burn your homework, you can't reverse combustion and get your paper back with all these precious notes on them. They're gone forever, irreversible. But some reactions are reversible. So let's take a look. Hydrogen plus iodide makes 2HI, hydrogen iodide. Let's open the tanks. Molecules start flowing in. Now, the reaction hasn't happened yet. I froze time, stop, and I just do a count. There are 7 greens, 4 blues, and 0 HIs because there hasn't been a collision yet. We can think of these as moles per liter, like 7 moles per liter. That's incredibly massive, a little unrealistic, but let's just go with it. Okay, now, let's say the reaction happens, there's a collision, and we switch our dance partners, we form hydrogen iodide. If I was to count now, I'd have 6, 3 blues, and 2 green-blue combinations, 2 hydrogen iodides. Let's say the reaction happens again. I freeze time, and I count where we're at now. I'm at 5, 2. There's actually 4 HIs on the screen. And now, let's say I let the reaction go again. I count when I freeze time. The concentrations have begun to level off. So that is what equilibrium is, when the rate of the forward reaction equals the rate of the reverse reaction. The same amount going forward as backwards. The amount going forwards equals the amount going backwards, so the concentrations level off. Here's what I'll try to show it on this screen. Here's what it would look like. So on the left, H2 and I2 crash together, but on the right, bottom corner, HI is crashing into another HI. When we switch the dance partners, we realize we've just created exactly what we had before. The rate of the forward equals the rate of the reverse. The concentrations are the same, 5, 2, 4. Here it is shown another way with Lego. Here is my first 2-minute Lego video. Ready? Here's another way to look at equilibrium. I used to play with Lego when I was a kid. So there's H2, see? 2 orange, or 2 H's put together. Here's I2, 2 I's. Let's count them. 1, 2, 3, 4, 5, 6. 7 moles per liter of H2, 4 moles per liter of I2. Okay, here's the forward reaction happening. Crash together, switch dance partners, and we form some HI. Now look what's happened to this pile. 1, 2, 3, 4, 5, 6 moles per liter of that. We used to have 7. 3, 1, 2. So this went down, and this has gone up. But I still have more of a forward reaction happening right now, so I'll do one more. Then I have a backward reaction. Now, let's say I'm approaching equilibrium. And notice I've got 1, 2, 3, 4, 5, 2, 4. Now let's say I'm approaching equilibrium and boom, I've hit equilibrium. How do I know? Well, the definition of equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction, which means this. At exactly the same time that 2 of these crash together and form this, okay, so that's going forwards. These 2 crash together and go backwards and form our originals. So these 2 went this way and these 2 went this way. Look at 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 4. The concentrations are the same. So every time one goes this way, one goes this way. That's equilibrium. Excuse me. Rate of the forward reaction equals the rate of the reverse reaction. There, 2 minutes. Now, what does this look like on a graph? You can see that the concentrations of the reactants went down and the products went up. When we graph it, it looks something like that. And a classic question that we can ask you is, At what time is equilibrium established? Time 0, 1, 2, 3, 4. So when the concentrations level off, that's when equilibrium was hit. Okay, so at time index 2, that's when equilibrium was established. Okay, now those are quite angular graphs. When we show these to you on tests and so forth, if we were to graph it real time, it would look a little more like this. Okay, so that's the first concept. So watch for the next video. What conditions are necessary for equilibrium to occur? Oh, fascinating stuff.